I'm Ryan, and in this video, I'll present work with my co-author, Caliskan, on bias in unsupervised computer vision models. If you remember anything from this video, I want you to remember one thing. That's that we found systematic evidence of human-like social biases in unsupervised image representations. Now, why should you remember that? In this study, we show that there is quantifiable bias embedded in not only supervised, but also unsupervised computer vision models. And this means that the biases we find are learned without any human labels or annotations. So in this video, I'll discuss how, even without structured classes, unsupervised models can still learn patterns of bias just from the ways that people are commonly portrayed in images. But more broadly, why do we care about bias? So here we're using bias as a technical term to describe statistical associations of concepts embedded in ML models. And associations about social groups can cause representational harms, such as stereotyping. And they may cause further allocational harms in the specific applications that these representations can be used for, including image generation and classification. The last thing you should remember is that our study is systematic. We measure biases with methods rooted in theory from social psychology, and we test for a wide variety of representational harms: racial biases, ethnic biases, gender biases, and other less frequently tested visual biases like weight stigma. We also develop new tests for intersectional bias, and our results are consistent with documented human bias and previous results from natural language. So to understand how unsupervised computer vision models can be biased and why that can be harmful, let's look at natural language. Recently, these new transformer-based models trained on large swaths of text from the internet, like this one, GPT-2, have drastically improved tasks like text generation. But lots of recent research has shown how these models can be biased. So here's a simple example of biased text generation by GPT-2, in which women are associated with sexualized careers, while men are associated with non-sexualized careers. Now, GPT-2, the model in question, was pre-trained on Reddit-based text. And there's a lot of great work in this conference and in other venues about how structural marginalization in internet data sources like Reddit can result in representational and allocational harms if data collection is done carelessly. Now, what does this have to do with computer vision? Well, in 2020, this new model, iGPT, was released. And iGPT has nearly the same architecture as GPT-2, but instead of training to predict word sequences, iGPT trains to predict pixel sequences. iGPT was pre-trained on ImageNet 2012, a well-known benchmark dataset. And this particular version of ImageNet contains 1.2 million images and 1,000 object classes, many of which contain depictions of people. GPT isn't the only new pre-trained CV model setting benchmarks. SimCLR, another unsupervised CV model released this year, uses a more traditional large neural network, but was also pre-trained on ImageNet. And the appeal of unsupervised models like these is that they can be used to produce generalized representations for images. And then these representations can be used to easily train smaller models for downstream tasks in a kind of transfer learning called fine-tuning. So for example, representations from both of these models have been used to train state-of-the-art supervised image classification models. In other domains like face recognition, there are very popular pre-trained models like FaceNet that serve a similar purpose, albeit with supervised pre-training. So how does this help us? Well, by producing high-quality representations of objects and images, models like iGPT and SimCLR allow us to, for the first time, quantify bias in images without any labels at all. And that leads us to our research question, which is, are these new computer vision models susceptible to the same bias and representation issues as their counterparts in natural language? Our approach to answering that question is rooted in social psychology, specifically a well-validated implicit bias test called the Implicit Association Test, or IAT. Now, the IAT tests for cognitive associations between two pairs of concepts. So for example, between white people and harmless objects versus black people and weapons. The test asks participants to quickly categorize words and images. And the theory is that it's cognitively easier to categorize stereotypical pairs, like black people and weapons, than it is to categorize astereotypical pairs, like black people and harmless objects. And the magnitude of cognitive association between the two pairs is measured by the average difference in reaction time on this categorization task. Given some of the similarities between human acculturation and machine learning from the internet, my co-author and her colleagues adapted the IIT to test for bias in machines, specifically natural language models. So instead of measuring the difference in a human participant's reaction time, the word embedding association test measures the mathematical similarity of concepts embedded in a natural language model. And these word embeddings are a representation of how a particular word appears in the pre-training corpus. So let's say we wanted to measure IIT style the stereotypical association of men with science and women with liberal arts. So first we would define a bucket of words describing each of those concepts. So for example, father is an exemplar of the category man, and math is an exemplar of science. And rather than defining these concepts from scratch, we just take these word buckets directly from the stimuli shown to human participants in the implicit association test. And then we can compare machine and human results directly. So once we define all these buckets, we extract an embedding for each of the words, and then we can use cosine similarity to test for a systematic association between the aggregate representations in each pair of buckets. So how can we adapt this test to images instead of words? Here's an example replication of the insect flower IIT, which tests for an association between flowers and pleasant attributes versus insects and unpleasant attributes. This is a good baseline for two reasons. First, psychologists consider this insect flower bias to be widely shared among humans. And second, objects like flowers and insects are very common in ImageNet, the pre-training data set, so we expect them to be well within sample for our models. So to perform this test, we first collect a bucket of images for each concept, a bunch of images of flowers, a bunch of images of insects, and then using a pre-trained model like IGPT or SimCLR, we extract a vector representation for each image. And we can think about this like dimensionality reduction from the number of pixels in the image to some d-dimensional embedding. Then we can use the same permutation test as in the word embedding association test to estimate a standardized effect size, or a unit of bias, d, and a significance value, p. And we'll call this the image embedding association test, or IEAT. We apply this method to replicate 14 implicit association tests, including, for the first time, 3 picture-only IITs and 5 mixed-mode IITs, including pictures and words. If you'd like to see all of the categories and the original human results for these tests, stick around to the very end of this video. Now, if we want to compare our results to human results and natural language results, we need to make sure that we construct our sets of stimuli to match the originals as closely as possible. And we need to collect multiple exemplars for each stimuli to control for any confounding elements in the images we choose, like colors or other objects. For the picture IITs, this is pretty easy. We can just use exactly the same pictures that were shown to human participants. But for the other IITs, we need to translate verbal stimuli, like father, into images. And to do that, we first look for a category matching the stimuli in CFAR 100, since both of our models were validated on this data set. But for the more complex verbal stimuli, like office, we search the term on Google and then take the first results that match a set of criteria for positioning, background color, size, and other potentially confounding factors. And you can see all these criteria, the search terms we used, and the images we collected in our code base. All of the categories in the IITs use exemplars that are fairly easy to visualize, but there's one notable exception, and that's the valence IITs. And here we're using the term valence to refer to the pleasantness or unpleasantness of a concept. 9 of the IITs we replicated test for the association of certain social groups with pleasantness and unpleasantness, so valence. But these are fairly vague concepts that might be hard to visualize in the abstract. Fortunately, many of the exemplars that were used in the original IITs, like beach or morgue, were also rated for imageability or imagery by human participants in a separate study. So to represent pleasantness and unpleasantness in images, we collected stimuli for the words with the highest imagery scores, like the ones shown here. With all these stimuli in hand, let's now walk through our results. So this chart depicts the effect sizes for each IIT we replicated for both models we tested. SimCLR is in pink and IGBT is in blue. Hollow circles in the chart indicate statistically insignificant results. So we first tested our method on the baseline insect flower test I mentioned earlier, and we found, as expected, that both models show a significant stereotype congruent bias, which is evidence that these models are encoding widely shared human biases. We also evaluated the specificity of our method by randomizing the images in each category, and we found that on these random tests, the rate of false positives in our test results approximately matched our significance level. So having done that, we moved on to replicating IITs dealing with racial and ethnic biases. And just like in humans, we found a significant bias associating Black people with weapons and white people with harmless tools. That's the weapon IIT. And we did this both for old weapons like maces and swords that were used in the original IITs and also new weapons like assault rifles. We also found a bias in IGBT relating lighter skin tones to pleasantness, but we didn't find a significant valence bias regarding European and Black Americans. We tested around for other ethnicities as well, and we found negative valence biases about Arab Muslims, mirroring recently published results for the GP2 language model. We didn't find any evidence of xenophobia towards Asian people or indigenous people of color. We also didn't find any valence bias against Jewish people, but a lack of significant bias in our test doesn't guarantee that the model is bias-free. So for example, insignificant test results could be due to the low sample sizes found in the original picture IITs. We also found significant evidence of gender stereotypes, including stereotypes associating men with careers and women with family. For IGBT, we also found associations between men and science compared to women and liberal arts. And finally, we found fat-phobic valence biases associating larger people with unpleasantness, but we didn't find any significant bias associating people who appear to have disabilities or depictions of certain sexualities with unpleasantness. We also examined biases at the intersection of race and gender. So we tested 3 hypotheses from social psychology about intersectional bias, and those hypotheses are shown on the left, while our results are shown on the right. The first hypothesis we tested is the race hypothesis, which posits that biases between racial groups will most resemble biases between the men in each group, because men are the culturally hegemonic gender. And this chart shows the extent to which white people, shown on the bottom axis, are associated with pleasantness, versus Black people, shown on the left axis, are associated with unpleasantness. And we break down those associations by binary gender group. We're using a gender binary here. We use it in the rest of our tests because those are the stimuli used in the original IITs. By the darker color in the left column, we can see that the magnitude of valence bias is much stronger when white women are involved. And consistent with the race hypothesis, the overall racial bias, which is shown in the middle box, is most similar to the upper right-hand quadrant, which is the bias between white men and white women. And that's exactly what we'd expect from the race hypothesis. Likewise, if we look at the extent to which the woman construct is associated with pleasantness, that's on the bottom axis, and the man construct is associated with unpleasantness, that's on the left axis, we see something similar. The overall gender bias in the middle box there is closest to, in magnitude, the bias between white males and white females. And this is an example of the gender hypothesis, which states that biases between gender groups will be most similar to the bias between the white people in each group, because white people are the culturally hegemonic race. From the negative effect size in the upper left-hand quadrant on this chart, we can also see that white men are considered more pleasant than Black women, despite the overall valence bias towards women. And this would be an example of the intersectionality hypothesis, which says that there will be emergent biases between intersectional groups that can't be explained by the overall race and gender biases. And in the same vein, this chart shows the association of males with career attributes and females with family attributes. And while the Black versus Black and white versus white gender stereotypes are very similar, we see in the upper left quadrant a higher emergent bias associating Black men with careers and white women with family, which may reflect negative stereotypes about Black men and family. So having seen all this, we asked, where is this bias coming from? And while the answer is complicated, we did make some key observations. So the ImageNet dataset is sourced mostly from Flickr, which is a large collection of internet images from many individuals. And a recent overhaul of ImageNet found that its categories or classes often unequally represent race and gender groups. And a similar study on the MS Coco dataset, which was also collected from Flickr, shows that the depictions of kitchens or homes coincide far more often with depictions of women than with depictions of men. Men are often more portrayed in industrial settings. So this might help explain why we observe gender career biases in image representations from ImageNet. Likewise, this study done on the ImageNet dataset, we can see how certain object classes have gender imbalances. So more men are portrayed with quote-unquote working dogs than women, whereas women are more often portrayed with tiny toy dogs or non-sporting dogs. And while this may seem innocuous because images in the dog class have seemingly nothing to do with people, our results show that even datasets dedicated to object recognition, like ImageNet, are encoding many biases. And ImageNet 2012 contains only a few categories specifically devoted to people, but depictions of people scattered throughout the dataset can still culminate in patterns of stereotypical portrayal. And we find that these patterns of portrayals of certain social groups are corresponding to many of the biases we observed in unsupervised image representations. To see how these patterns of stereotypical portrayal could make their way into a model and its output, let's look at one final example, and that's image generation. So just like GPT-2 can auto-regressively complete sentences, IGPT can complete images with high accuracy, just like this pigeon. Now, what if we asked IGPT to complete an image of a person? We fed in a cropped image of an artificial face that appears to be male. And of 40 completions of 5 different faces, 42.5% feature suits and career-related attire. One of them proudly displays a fish, and one even holds a gun. But when we use a female-appearing face, over half of the completions wear bikinis or low-cut tops. And it's likely that this bias is coming from the many classes for bikinis and bras in ImageNet, many of which Prabhu and Burhani, the study from the previous slide, found to be verifiably pornographic. And this result is a reminder of the example from the very beginning of this presentation of sexualized text generation. And it's easy to see that IGPT, a pre-trained computer vision model, can be just as biased as GPT-2, a large language model. So now that we know these models are biased, what next? Some of the limitations of our methods could lead to future work. So for example, the models tested here are open source only, but larger, newer proprietary models are still being developed. For example, the XL version of IGPT, which is not publicly available, was trained on 100 million additional web images that are not publicly available. A similar model will appear in ICLR this year that was trained on the mysterious proprietary JFT dataset of 300 million web images. And it'll be interesting to see how these larger datasets affect representation biases in pre-trained models. Secondly, in this work, we replicated existing IITs, but a lot more work needs to be done on other normatively pressing bias issues. And work needs to be done to modernize the categories and stimulus used in the original IITs. So for example, we might want to include non-binary gender groups or other ethnic groups that weren't tested here. And of course, our method is limited to concepts that can be visualized. So it's difficult to quantify visual bias about symbolic or unobservable categories. That remains an open problem. It's also not clear exactly how these representation biases will affect deployed supervised models. We give an example, but for practitioners, we advise greater precaution using pre-trained models. Consider and catalog representation issues before, during, and after data collection. Conduct extensive auditing for the harms considered here and other harms that we didn't consider. And above all, practice value-sensitive design throughout the building and deployment process. If you have any questions, feel free to contact me or visit this site for our code, data, and other materials. And before I wrap up, I'd like to give a special thanks to my tireless co-author, Eileen, our colleagues and reviewers for their feedback, and of course to you for making it all the way through the video. Thank you.